Good morning, everyone. This is Thursday. This is the fourth lecture. The plan for today is to go over some material about simulations of Markov processes. So I'll be sharing my screen quite a lot today to show you some Jupyter notebooks that I have about simulations. Everything I'll be discussing is in the Dropbox, so it's part of the courseworks that are linked to all the chapters that you have, the 5 chapters. And then we've seen some material from the 5 chapters. So today we'll go over the material that covers simulations of jump processes and stochastic differential equations. But before I get there, I want to just show you how we get random numbers from a computer and how we build histograms. And these will be the main 2 tools that we need numerically to start analyzing simulations and the simulation of Markov processes. So I'll start with sharing my screen with something that is on the Dropbox, which is a list of random number generators that you can use either in MATLAB, in Python, or in Mathematica. So I'll be talking about Python mostly. Well, actually, all the Jupyter notebooks that I'll be discussing and the ones that you have available on the Dropbox, they're based on Python. And so in Python, you have various random number generators that are part of the library or the package NumPy. So you'd have to append numpy.random to get a random number here. So the uniform random number generator, which is the basic one that you can use for generating other types of random numbers, is the uniform one. And in Python, it's just random or rand. In MATLAB, it's rand. So sometimes you have many notations in Python for the same random number generator. And I'm showing also Mathematica if you're more familiar with Mathematica. The one we'll be using a lot is the 0, 1 Gaussian random number, and that's random n, which is the same in MATLAB, or you can also use standard normal with this, and that will give you a real random number distributed according to a Gaussian of mean 0 and variance 1. If you want a certain mean and a certain variance, you can use this one here. Okay, but you have many other ones related to other types of random variable like the exponential, the Bernoulli, binomial, Poisson, Cauchy, and then you have many, many more. I'm just here showing the most common ones that you might want to use. Now, the one thing I won't be discussing is what's behind those functions. How do we generate random numbers on a computer? How are random numbers generated on a computer? This will be the subject of a whole course. In fact, on the computer, we don't have truly random numbers. We have what we call pseudo-random numbers, but they're good enough for simulations, and for the purpose of simulations, they are just random enough. And then the good thing about this is that we can generate them very easily, very quickly, and then we can also redo a simulations using exactly the same random numbers using what we call a seed, but I'm not going to talk about this. So for now, for the purpose of this course, I'm just assuming that we have access to these generators, and then we can use them. And we can call these black box functions to get random numbers. And these random numbers, of course, we need them to do simulations because we want to mimic noise, we want to mimic randomness on the computer, so we need to be able to generate random numbers. Okay, so that's the first ingredient that we need for simulation. The second ingredient that we need for simulation is to be able to build histograms, and for a given set of random numbers, so for a given sample, we want to be able to calculate expectation, variance, and visually actually to see a distribution of that sample. You could write yourself you could write your own histogram function if you want, but it's already available in Python, and then I'll be showing this in a minute. But before I do this, I'm just going to go on the board and explain what is a histogram and what I mean when I say that we have a sample and then we want to build a histogram of a given sample. So I'm just going to switch on the camera now. So I want to cover the notion of histogram. This is part of chapter 1. It's section 1.8. So I'm actually following my own lecture notes again, and then in that section. So what we have is a given sample. A sample is a collection of random numbers. and I'm going to have L of them. So L is the sample size. And you have to imagine that L is quite large. We might have 1 million sample, and then we want to calculate a histogram. So what's the histogram? The histogram is just the distribution of these values. So these are the possible values, and I just create some boxes, and then I might have that many values here, that many values there, and then so on. Okay, so I want to see the distribution of these values. And maybe I want to compare this with some theoretical distribution, which might be, for instance, a Gaussian. Okay, so the dotted line will be the theory, but I want to construct now this histogram, which is what we call also the empirical distribution of the sample. And the meaning of this, I think, as many of you know, is that the height of the bar will be proportional to the number of sample values in that box. So here we have a certain value and then a certain bin size delta x. So in the box x, x plus delta x. So the histogram will be defined by two things: the range over which you want to build the histogram, but also the box size, which is also called the bin size. This sometimes in some Python functions will be set automatically, but otherwise you can set this yourself. Okay, so what do we have? We have, I will define various things. So the height of the bars there is what is the number. So this will be the number of sample values, or the number of sample in the bin x, x plus delta x. Okay, so that's the number of samples that falls into that box of size delta x, and I use my sample of size L. I put the hat there because in statistics we put hat whenever quantities have to do with a sample. Out of this, so this is normalized. If I sum this, I'm going to get L. Out of this, I want to build a distribution which is normalized. And to do this, I'm just going to write, I take the L, the N I mean, and I normalize by L. Now this is a distribution. If I sum over all the boxes, I'm going to get 1. Out of this, what often we want to do is to get a density, so an empirical density, and this will be, what you do is that you take the distribution and then you divide by delta x. So that means that you take the histogram, the actual bare number of samples in each of the boxes, you divide by L, and then you divide by delta x. This has the interpretation of a density because if you sum over the boxes and you multiply by delta x, so that will be a kind of Riemann integral, then you're going to get 1. Okay, so by normalization, what you have is that the sum over the boxes of this multiplied by delta x, this will be equal to 1, and that's the normalization you want for the histogram. Okay, so this is quite basic, but it's very important because we'll be doing simulation and I want to see the distribution of the path or the realization of the process. So I need to be able to build a histogram of that, and then you have to be clear about what the histogram really means. So I have a given sample. This could be trajectories, this could be just points, it could be just Gaussian random numbers, and then you can call the histogram function and then you're going to get something like this. But you have to realize that what you get out of Python or any routines will be empirical density, which is normalized in that sense. Okay? And this also gives you a kind of working stream out of a sample. What you do is compute this, compute this, compute this, and then you have this quantity. Okay, I'm going to show you how this works in Python. So now I'm going to share my screen again. It's here. Okay, I think now you see the Python notebook. This is a Python notebook that I've put into the Dropbox. It's just a little notebook that shows how to build histograms in Python. And I took this, you have two references there. I'm loading NumPy. NumPy is a package that contains many useful mathematical functions, and then I'm loading matplotlib. Matplotlib is a package to do plots. Okay, so what I do here is I generate 1,000 random numbers, which are Gaussian random numbers because I'm calling NumPy random n. So these are Gaussian random numbers. So I do this, it's very quick, I generate 1,000. I can see them, so this is actually the histogram, but this is the visual histogram. If you only want to see the visual histogram, then you do this. Here I'm plotting the histogram of the data using 100 bin, and I do density true to normalize according to the density that I've shown on the board. So this is normalized as a density, and I do PLT show to show the plot. So I have 1,000 sample, and this is the distribution. It's not exactly Gaussian because I only have 1,000 numbers. If I go higher, for instance, if I have 10 to the 6, so 1,000,000 sample, it's going to take a bit longer to generate, but it's been done. And now if I do the histogram of this, you see it's very close now, it's very neat. It's a Gaussian distribution of mean 0 and then standard deviation 1. Okay, but you're never going to get something as clean as this because you're not going to have so much data. Let's go back here. I'm going to have 10,000 instead. And if I plot the histogram now, I see something that looks like a Gaussian, so I can compare this with theory. But of course, it's a given random sample, so it's not exactly Gaussian. That object is a random object. If I generate a new sample, I'm going to get a new empirical distribution. Okay, so then I show how to use histogram to get different specifications. So there are two functions in Python to get histogram. There's hist, and then there's histogram. And histogram has just more parameter. You can specify the bin size, the bin position, and then so on. So here I'm just showing this. I'm not going to go over this now. Have a look at that notebook, and then you'll be a pro now to just build histogram. And I'll be using histogram quite a lot when I do simulations. Good. Okay, so that's for histogram. And now what I want to cover, I'll go back to the camera, is to cover Monte Carlo simulation. So sampling. So what we'll do is that we'll generate various processes. So we're not quite there yet, but we'll get there. And so the other ingredient I want is what we call statistical sampling, or in physics, we call this Monte Carlo sampling. Sanjib, can you confirm you see the board now? Second point I want to cover, actually the third point, is Monte Carlo sampling. So the purpose of Monte Carlo sampling is that you have a random variable and you want to compute some expectation of that random variable, which we'll denote by this. Okay, and this could be either the sum over the values or the integral of the PDF over the values. Okay, depending on whether you have a discrete or a continuous random variable. Okay, so the way we do this numerically is that we just build a sample of values for the random variable, and then we use an estimator to estimate the expectation. So the Monte Carlo estimation of the expectation has various steps. The first one is that you generate your sample. So you generate values just like we had before. You generate L of them according to the distribution. So just like I did in the Python notebook, I can generate 10,000 Gaussian random numbers. And what I do is then calculate the estimator. There are many possible estimators that you can use, but the natural one is usually, I'm going to actually write this as mu. There's a mu hat because it's estimated from a sample, and it would be 1 over L, the sum from 1 to L of the actual values. Okay, so this is a mean. I think it's very natural in physics. If you're doing many measurements, you're taking the mean of the measurement to get an estimate of the physical parameter that you're trying to measure. But it comes from statistics. You just have a sample, and then the estimate for the mean is the sample mean. Okay, and it's that sum there, divided by the size of the sample. The reason why we use this estimator is because if you have a very large sample and larger sample, then it converges to the true mean. And this is the law of large number. The law of large numbers. It says that the estimator with calculated with L samples will converge to the true mean, the true theoretical mean when L goes to infinity, and this is convergence and probability. So the probability that you do not converge goes to 0. So the statement mathematically is that the probability to be away from the true mean, or to be away from the true mean, that goes to 0 if you take the limit L going to infinity. So this just tells you that if you look at the distribution of the estimator, it's more and more concentrated onto the true mean, and so that justifies taking an estimator to estimate a theoretical quantity. So if you don't know the expectation of a random variable, what you can do is just generate many values of that random variable, many realizations of that random variable. You take the estimator, and if you have a very large sample, the law of large number tells you that you'll be very close to the true expectation. Okay, now this is good, but you want also to give an error for that estimation, and the error for the estimation will come with statistical error. I don't want to discuss too much here, but the error that you make is part of the section, just the section after, so this is the section 1.13. The error that you're making is that mu, the mu L, the estimator that you have, is plus minus sigma L away from the true expectation. So, and this is a Gaussian error that you're making. And I think you're also familiar with this. When you're making a measurement, a physical measurement, you take the sample mean to say this is my estimated value, but you calculate an error bar around this using Gaussian error bars to say, well, that estimated value falls in that range with some confidence. So that's the confidence interval. And the sigma L here is the empirical standard deviation of the sample, and this is 1 over square root of L. You have the big square root here, and then you have 1 over L, the sum of the squares, minus the empirical value that you had for the mean. Okay, and so this is the estimated standard deviation of the estimator that comes from the independent samples that you have in that collection of values that you have. So there are two things, and I'm going quickly on this, but have a look at the lecture notes. You have a sample, you have the estimator for your mean or the expectation, and with this, you have an error, which is a Gaussian error that is estimated as the empirical standard deviation of the sample. So this is the empirical second moment minus the mean squared, so that will be the estimated variance. You take the square root for the estimated standard deviation. So what you get is a point with an error bar, and the error bar is sigma hat on that side and sigma hat on that side. That's the usual confidence interval that you will actually write. If you want to be more precise, you can take a 2 sigma error bar, but here we'll just use sigma error bars. Okay? Okay, I think there's some questions here. Yeah. Okay, I'm assuming now the focus is better. I hope it's better.
Yeah,
I'm using
better.
a cable for the internet, so it should be okay. I'm not using Wi-Fi or anything, so But of course, we're in South Africa, right? So South Africa is part of Africa. The connection is not always quick. Okay, so I've covered random numbers, histogram, Monte Carlo sampling, and statistical errors. Now I've got everything to start doing simulation. And what I'll do is I'll start doing simulations for jump processes. We could start with discrete time Markov chains, but if you know how to simulate a jump process or a continuous time Markov chain, then you know how to simulate a discrete time Markov chain. So I'll go directly in continuous time and then show you how we can simulate jump processes. Right. And then with this, we'll see some examples. And then I'll go to simulations of stochastic differential equation, which we started seeing actually yesterday, and I'll show you some examples also on the Jupyter notebook. Good. Okay, so here I'm going to do simulation of jump processes. This is part of my lecture notes in section 3.8. So this is chapter 3 on continuous time Markov chain, and this is section 8. There are two methods you can use for simulating a jump process. There's the first one, which is the discretized time method. What you're doing for this one is that this is your process that you have. And what you do is that you discretize your time in time steps of delta t. And then you're going to have n of them. So n will be t over delta t. And what you're doing basically is that you're simulating the jump process as a discrete time Markov chain in time steps of delta t, which is quite natural. We'll be doing the same thing for stochastic differential equations, and then you just collect all the points, and that will give you an interpolation of your continuous time process. If delta t is small enough, you'll be fine. Okay, so over one delta t steps, then you need to generate a point according to the probabilities, the transition probabilities of the jump process. So how do we do this? So this is the transition probability. So we know, we've seen this on Tuesday, that the probability of jumping from I to j in delta t was the transition rate wij times delta t, because the transition rate was the probability per unit time. Okay, so the algorithm now, and so if you know this, so you have all the transition rates, so this is given to you, and then you want to build a simulation of the corresponding jump process. So what you do, and this is the algorithm, first you start at some state, I, that's the initial point, so this will be x0i, that's the initial condition, and then you attempt a jump to a state j with probability wij dt. So basically, if you sit at I, you look at all the possible j's that you can jump to, you have the probability for jumping to each of those j, you have to choose a j proportional to the probability that is given like this. So you can do this numerically, and then you update your state. Update. Then the new state at time delta t will be j if the jump is accepted, otherwise you stay at I if the jump is not accepted. And then what you do is that you just repeat. Okay, so you're going to have a loop of size n. You start somewhere at state I, You look at all the possible j's on which you jump. You can jump. They each have their own probabilities of being reached. You choose one at random. You leave the computer choosing at random the state j, and then you jump on that j. This is your new state. Now you're on that state, you do the same. From that j, you look at all the possible places you can jump. You have the probability for this. You leave the computer choose a possible next state according to the probabilities that are given to you. So the choice is not uniform random. It has to be proportional to the probabilities transition rate times dt. And then you jump there. Okay, maybe you stay here. Maybe you stay, maybe you jump, maybe you stay, maybe you jump. And so at the end, what you have is a kind of interpolation of the process. If delta t is small enough, you'll get a trajectory, a random trajectory of the process. Okay, so with this, what you'll get is indeed one trajectory, but you can repeat this many times to get many trajectories. So what you'll get, for instance, for a Poisson process is something like this. You'll get one trajectory of the Poisson process, and the Poisson process is actually covered in the coursework, so it's asking to simulate the Poisson process, and then you'll get one trajectory. You can repeat this with another trajectory. And then you'll get something like this. Okay, maybe I interpolate so that you can see it. You can get another trajectory. So these are random trajectories of the process. They are what we call path realizations of the stochastic process.
Hugo, there is a question on the time.
Yes.
There's a question in the chat on the choosing delta t, I think.
Yes. Yes, I'll come to this in a moment. So the way you have to see those trajectories is a sample of trajectories. So before we had a sample of real numbers. For instance, in the Jupyter notebook, I just had 10,000 real numbers. But now, as you do a simulation, you can keep all these trajectories, so you have effectively a sample of trajectories. And now you can do whatever statistics. You can build, if you have enough trajectory, you can build a histogram at a given point, a histogram at the final point, and so on. So you can start doing statistics, statistical analysis of the sample of trajectories that you have to characterize the process. You can even do prediction because you can simulate the process up to some time t and then say, what is the probability that I reach a given state at time t? Well, if you cannot do it analytically, then you can do a simulation. You just propagate, generate many paths up to the time t, and then you just count the number of paths reaching the state that is of interest to you, and this will be proportional to the probability of reaching that state. So you can do a histogram at that time to see what is the probability of reaching that state. So simulation is crucial if you want to do prediction. This is something general in physics. I've mentioned this before. The number of models for which you can do analytical calculations is very, very limited. You have to do simulations if you want to go to realistic physical models and complex models involving many different states, and for instance, if you want to simulate interacting particles. Okay, so there's a question here. How will changing the size of delta t affect the feasibility of the simulation? So this is a crucial point. Delta t has to be small enough, but not too small. If you take delta t to be 10 to the minus 6, it's too small. It will take too long to actually generate the trajectories. So this is something that you have to experiment with. There's no like universal answer about what is the delta t that you should be using. People tend to use 0.01 or 0.001, but it depends on the rates. If the rates are really large, then you have to use a smaller delta t in general. Okay.
I guess one rule is that sum over wij times delta t should be much smaller than 1, I guess, right?
Yes, delta t should be much smaller than 1, but moreover...
No, I'm saying sum over wij times delta t should be much smaller than 1.
Yes, exactly. So this has to be a probability. So if you take the largest rate and you multiply by delta t, this has to be smaller than 1. Okay, so that's the prescription. But otherwise, you generate this. Now, what's going to happen, actually, you'll see this in simulation, is that most of the time you do not jump. Okay, so here if I have this plateau, you see I have different delta t's and I haven't actually changed states. So in simulation, in many cases, over the delta t's that you simulate, you do not jump. So you're spending lots of computational power for actually deciding not to jump. And so there's a better way to simulate jump processes that doesn't use that delta t. So this discretized time method is kind of nice, it's clear, we can understand it, but it's not the best way to simulate a continuous time process. So there's a second method, which is the random jump method, which I want to discuss now. The second method that we can use now is based on the idea that a jump process is just a collection of random times and jumps. So this is the second one. It's the random jump time method. It's also called sometimes the Gillespie method, but it was in simulation literature way before Gillespie. So what you have here is, remember, a jump process is you stay into some state, you jump into another state, and then it's a collection of staying in a given state for some random time and then going into another state and staying there for some random time, and then so on. So a jump process is a collection of occupation time and the state that you occupy. And then we've derived this on Tuesday. The occupation time is an exponentially distributed random variable. So what I can do is that I start in one state, I generate an occupation time according to the exponential distribution, I stay in that state for that time, and then I choose another state at random according to the transition rates, I throw another occupation time, I stay in that state for that time, and I repeat. Okay, so I'm going to write this. So essentially what you can do is the process that you have from t0 to capital T, if I denote this by capital T for that T, you can decompose that trajectory as a sequence of visited states, okay, with a sequence of residence time for each of those states. And those residence times are exponential. So these are the states visited, and these are the occupation time for each of those states. Okay. So I have the occupation time. These tau i's, they are exponential random variables with the escape rate Ri. So the time that you stay in the state I is exponentially distributed with the escape rate. The jump probabilities between the different states is given by Wij divided by Ri. Okay, this is a result that we haven't seen, but this is when you're finished staying in a given state, you have to choose another state at random. The way the probabilities for choosing that state is proportional to the transition rate, but you have to divide by Ri in order to make this a normalized probability. So the algorithm for this one now is algorithm. You start again in some state, so you start x0 in some state I. You generate the first time t1 according to an exponential distribution of rate Ri. And you can do this on a computer. There is an exponential random number generator on Python or any language like MATLAB. And then you attempt to jump at the end of the time, you attempt to jump to a state J with probability Wij divided by Ri. So you're at the state I, you want to jump to some of the possible j's that are connected to I. You do this with some probability given by this, and then you update. But now you don't update at the delta t, you update after the time t at tau 1. And then you repeat. And this is a lot more efficient because you see, you're not going to do each simulations for the delta t. You really keep the state all the way down to the occupation time, which is random, and then you jump. So you're really carrying only, you're doing a jump when you need to do a jump. And then you stay there here, you throw an exponential random variable to stay here, and then you choose another state at random, so you do a jump. And so what you generate is a bunch of visited states and then their occupation time. And this is very, very efficient. Okay, especially if you want to do long time simulation, this is the method that you should be using. Okay. That's as much as I want to say for the jump processes. Have a look at the coursework for chapter 3. There are some simulations of jump processes there. So for instance, the Poisson process, which is probably the easiest to simulate. Okay, and then you have the Python code. It's really based on this. Yes?
Yeah, so you said that we generate tau I to stay in the state for some time, and then we propose a move to jump to state j. But when we are proposing it, it can accept the move or it cannot accept the move because it happens with probability.
No, actually, here you have, it will be accepted, right? Because you have to jump. The deal is that as you generate the occupation time, you'll be staying in that state for that time. But after that time, you have to jump somewhere. Okay, so
but as you have written in the board that we attempt to jump to j with probability this one.
Yeah, so maybe what I should write is that we should select j to jump to with the probability wijri. Okay. And
so we are just selecting the site where to jump to.
To jump somewhere.
Okay.
I think that's clearer. Thanks.
Yeah, thank you.
Why Gillespie method is better than the fixed time jump method? So the fixed time jump method, again, if we go back to the jump, the delta t method, the delta t method is that if your delta t is very small, the w, remember that the probability of jumping will be proportional to this. So if delta t is very small, this is very small. So the jump probabilities are very small. So most of the time you do not jump. If I simulate this with the delta t method, all these times here, I'm forcing the computer to decide whether to jump or not, but I'm not jumping. So this is what you see in simulation. So you're going into the loop of choosing whether to jump or not, but the jumps are mostly not accepted. And for some times they'll be accepted. So the computer is spending a lot of time deciding whether to jump or not to jump, but the answer is that most of the time it doesn't jump. So to bypass this, you use the random jump time method because you know you'll be staying there for an exponentially long time. So you should just use that property in the simulation built in, and then you're skipping that step of using delta t. Moreover, this is better because it doesn't have delta t in. So if you use a simulation with delta t, you might not be satisfied because you didn't choose a delta t small enough to begin with. So then you do another simulation with a smaller delta t. Then you think, oh, maybe I should use an even smaller delta t, and so you do another simulation. This method doesn't have any delta t, so it's a perfect simulation of the process. There's no approximation involved in simulating the process. The trajectory that you get are the actual trajectories of the process, random trajectories of the process. How to see proof that this method simulates the master equation? Well, it simulates the master equation because you're choosing all the jumps according to the transition rates. And the transition rates are the rates that define the master equation. So here, you're not solving the master equation. You're just generating multiple paths of the process. But if you generate many paths and then you look at the histogram, you'll see that the histogram evolves according to the master equation. Okay, so here we're not solving the master equation. We are generating paths, random paths of the process. We are generating realizations. If you want to go now into the distributions, what you should do is to generate many such paths. So maybe I should explain this. This is a good point. I'll do this with some other notes I have here. Then there's a question maybe I should answer. What if this is greater than 1? This cannot be greater than 1. Why? Because by definition, the rates are actually obtained by summing, right? Remember, the rate for I is the sum over j of this. So if the rates are positive, they're any positive number, and so this will be consistent to define the probability. So when I sum over j here, I get 1. So this is always a probability. There's no approximation involved in this. This is an exact result. Okay, so let me show you how you would actually calculate a histogram with this type of simulation. So there are two ways you can do a simulation to get histograms, and especially if you want to calculate a stationary distribution. You have parallel simulations, and then you have energodic simulations. So parallel simulations, what you do is that, and this will be applicable to diffusion. It's not just applicable to jump processes, it's also applicable for diffusions. So what you do is that you have a stochastic process, and then you have your time, and you want to simulate this over the time capital T. So you simulate one trajectories, and here it's easier for me to draw just some kind of random path, but it's not the path of a jump process, but it's just the path of a stochastic process. Okay, that's good. Then I'm going to generate another one. Then I'm going to generate another one. So you have to imagine now that I have many such paths, okay? Maybe I have actually 1 million paths. The good thing with computers is that they never complain about computing. If they were complaining, we would have a problem. But we can just compute stuff and then just let them compute for even an hour, a week, a month, a year, it doesn't matter. So you can push the computer up to your own patience. So the number of paths that you will be able to simulate depends on the power of your computer and then your own patience. Okay, so suppose I have many paths. What I can do is that I can slice now these paths at one time and say, oh, what's the histogram of those paths? So namely, with those paths, I can generate a histogram. So maybe I'll get something like this. Okay, and that will be the histogram at that time. So this will be at the time t. Okay, so I slice, I have many points in that slice, I have a sample, with that sample I can build a histogram. This is an approximation of the pxt. This is a finite sample approximation of the time-dependent distribution of the process. I can redo this at a later time, maybe t prime. And so maybe at t prime, I have now something else. Okay? And it's going to evolve with time. And you ask yourself, what is the evolution of this? Well, it will be the master equation or the Fokker-Planck equation. So what you see is really a computational reconstruction of the evolution of the probability density of the process that you reconstruct using a sample of path that you can slice at different times. So what you should do in the computer is to actually keep in memory all of these paths. It's quite big. If you have a delta t which is very small, you might have 1 million time step, and then maybe you generate 1 million trajectories, so you have 1 million times 1 million points. But that's fine, the computer can handle this, there's no problem. And that with this, you can slice at different times, calculate a histogram, and then you'll see the evolution of that histogram in time. Now, if you want to calculate the stationary distribution, what you should do is that you should do this for longer and longer and longer and longer times. And then what you'll see is that the histogram at some point stops changing. It just starts being the same and the same and the same, and that's the sign that you've entered the stationary regime and that you've reached the stationary distribution. In many cases, that convergence is very quick. You don't have to go to astronomical times to reach the stationary distribution. For a process, sometimes 10 equals t is equal to 10 will be enough. Sorry, that. Some sun suddenly. Okay, so this is one way to get the time-dependent distribution and the stationary distribution. It involves the simulation of a lot of different paths. If you're dealing with an ergodic process, this is simplification. If you're dealing with an ergodic process and all you want to calculate is the stationary distribution, then you can simulate one path. And this is great. And I'll just finish on this for this type of simulation. You can do what we call an ergodic simulation. Instead of simulating many paths, what you'll do is that you simulate only one path. So you start somewhere, you do your simulation, and what you do is that you slice your simulation in delta t, and then you just keep the points at those delta t's. So these points will actually form a sample from 1 to n, and n will be your capital delta t, the final time for your simulation, divided by delta t. These points are collected at different times, okay? And what's amazing for an ergodic process is that if you do a histogram of this, of these points, so you have n of them delta x, x, if n goes to infinity, if n is large enough, this will be the stationary distribution. Okay, so this is very economical because you simulate only one long trajectory, you collect all the points and steps of delta t. Chances are you've done the simulation already with delta t, so you're just collecting all the points that you've generated numerically. You build a histogram, and if time is large enough, and again, it doesn't have to be infinity, it's a question of doing a convergence analysis. If time is large enough, this will be very close. This will be an approximation of the stationary distribution that we were talking about yesterday and Tuesday. Okay? So you always have these two choices depending on what you want to calculate. If you want to calculate the time-dependent distribution, there's no other way. You have to do a parallel simulation. If all you're after is a stationary distribution, you can do the parallel simulation, but if you're dealing with an ergodic process, it's much better to do the one simulation trick, and then you collect all the points to get the density. Okay? Now, there are different parameters you see here. Here you have n, that's the number of points that you're generating. Here you have two parameters. You have time and the number of simulated trajectory. So L, that's the sample size. And so that's equal to the number of trajectories simulated. So in your code, you would always have these parameters, and as you're redoing simulations, you always have to vary those parameters to get better statistics, or to fix delta t, fix L, see if you have convergence, and so on. Okay? And then you'll see this in the simulation in the Python notebooks that I have. Okay? Okay. Okay, the last topic I want to cover is the simulation of stochastic differential equation, and then for this one, I'll really go into the Python notebook and then show you explicitly what you have in terms of results. Okay, and then this is going to be quick actually on the blackboard because we've seen how to simulate a stochastic differential equation yesterday. What we did yesterday was to write down the Euler scheme for the stochastic differential equation, and the reason we've done that is not because we were interested in simulating the SDE, but we were interested in understanding what an SDE was, or is. So, but the Euler scheme gives you the recipe for simulating an SDE. So I'll just put the Euler scheme again. and then I'll go directly to the Jupyter notebook to show you the result of the simulation. So this is a simulation of SDE. It's very similar to the jump process with the delta t. So we start with an SDE. So an SDE, we recall from yesterday, is an infinitesimal difference equation for some state that has some deterministic part plus some noise. And the noise will come from increments of the Brownian motion. And here I'm going to multiply the Brownian motion by sigma because I want to tune the noise amplitude. So sigma will be a real parameter. I can make this 0, I can make this small, I can make this big. I want to see the influence on the noise on the differential equation part. The Erder scheme for this, so the Erder-Maruyama scheme is the xt plus delta t, so there's going to be a delta t here, is xt plus, you time step with the deterministic part first, and then you add the noise in the way that we explained yesterday with z, and z is standard normal random variable. And so you start with x0 at some point. With this, you're going to get your state at delta t. Then you time step to get 2 delta t, and so on, all the way to n delta t. So you're going to have n points, and these n points will generate a trajectory, a time discretized trajectory, basically a broken trajectory like this. Okay, I'm not drawing this in the correct way. We'll see this. And if the delta t is small enough, if it's fine enough, then you're going to get your trajectory, your random trajectory. Okay? So there's no other way to simulate a stochastic differential equation. You have to use a delta t. So it's based on that delta t. And again, as a practitioner, as a coder, you have to ask yourself, how small should delta t be? And then this is something that you have to experiment with. The 2 questions here. Actually, there were some questions. I'll go with this. Okay. Tau is going to be a fixed number for a given state. No, tau is a random variable, right? Tau is the residence time. So you have to generate a tau, the residence time, as a random number according to an exponential distribution. So you have to use the exponential random number generator for tau. So you'll be throwing random taus every time you reach a state. Another question, how we do things, correlation studies when doing the holding time simulation. Correlation studies, I'm not sure what you mean by this, but if you have different trajectories, you can start actually calculating correlation functions if you have big enough sample of trajectories. So once you have trajectories, you can do any sort of statistical analysis. You can calculate correlation function, distribution, time-dependent distribution, stationary distribution. When does fixed time jump processes like discrete and random converge to each other? I'm not sure what the questions is. So a continuous time random walk is very similar. What you do is that you stay for some time in a state, and then you just choose to jump to another state at random. So actually a continuous time random walk is a jump process. So the simulation method that I've presented is also applicable to continuous time random walk. It's no different. Okay, and a discrete time random walk is just a random walk and discrete time. So here you don't really stay in a given state for a given time. What you do is you choose to jump to any other state at each time. That will be a Markov chain. Okay, then if I'm interested only in averages, a single trajectory enough? It depends. If you want the ergodic average, then a single trajectory will be enough. If you want the average, the expectation with respect to the station distribution, then you'll do a one trajectory simulation. If you want, now I've erased the picture here, but if you want the expectation with respect to a time-dependent distribution, then you have to use the parallel simulation method. What should the size of the histogram be in relation with delta t? Not really. The quality of a histogram depends on the size of the sample. So you always have these two parameters. The size of the sample, which is the number of trajectories that you simulate, and the delta t, which is a quality factor for the simulation itself. The true process is in continuous time, but of course computers don't have continuous time. So we have to discretize everything for computers, and so you have to choose the delta t. Delta t is not related to the number of times you redo the simulations to generate new trajectories. So they're completely different. And the quality of the histogram, again, is always a function of the sample size. Think again of the example of the 10,000 Gaussian random numbers that I had in the Jupyter notebook. If I choose only 10 numbers, for sure the distribution won't follow the theoretical Gaussian distribution. I need a big sample to see an empirical histogram that follows what I'm expecting. So the bigger the sample, the better in terms of quality of distributions. Okay, and I think this, in parallel simulation, there'll be different f for different trajectories. What is f again? Not sure what f is. Then are there practical suggestions for trajectories generation parallel, like what sort of random number generators to be used? No, so here I'm just assuming I can call the Python functions. I don't care about what's behind those black box function, right? I'm not trying to optimize time or anything. If you want to program things then in C or C++ or Fortran, you can actually choose different random number generators. But here, I don't mind about this. And to be honest, these days, things have been programmed so efficiently that you shouldn't care either. The random number generators that are available in Python are established, optimized random number generators that are very quick. Python itself is not very quick for simulation because it's not a compiled language, but the random numbers are standard, just like they are standard also in C and C++. Although in C and C++ you don't really have standard random number generators, you have to program those generators yourself, which is not so good. F is the distribution. Okay, yes. So in parallel simulation, there will be a different for different trajectories. No, the F is constructed from trajectories. Oh yes, so if you generate new trajectories, of course, you'll get a different F, right? Just like if I have a sample and I regenerate the sample, the histogram of that new sample is different from the histogram of the previous sample. A histogram is a random object. It's just a reflection of the random sample that you have. Again, if the sample is big enough, the F will represent something meaningful in terms of prediction, in terms of probability. But if I generate some trajectories and I regenerate trajectories, then I'll get empirical distributions that are different. The hope is that if the sample is big enough, it represents something that is close to the theory. Suppose for a process that the residence time is not exponential but something different like a power law, then one can find a scheme similar to the every delta update approach. The answer is no. So what we've seen is that, and this is quite a technical point about Markov process, what we've seen is that a Markov process, a discrete state continuous time Markov process, so a John process, has exponential distributed residence time, occupation time. And this comes from the Markov property. We haven't really dwelt on this, but it's a consequence of the Markov property. If you define a new process using residence times that are not exponential, it's a non-Markov process. So you cannot use that delta t procedure to simulate the process because you don't have transition rates that are meaningful for that process. So again, if the waiting time, the occupation time is not exponential, you break the Markov property. So the process is not described by transition rates. It's not a Markov process. What is the motivation for doing parallel simulation? The motivation is to be able to get the time-dependent distribution. If I want to get the time-dependent distribution of a Markov process, I need to do a parallel simulation because I need to build a sample of points. If I want the distribution at time t, so this is a theoretical distribution. It follows the master equation or it follows the Fokker-Planck equation. If I want to simulate that distribution, what I need is a sample of many points representing that state. So I need to simulate the process up to that time and collect many samples. So suppose here this is my time. I'm going to have here n times delta t. I'm going to have many samples of values. I'm going to have L of them. This sample represents the state of the process at the time t. You see, I time step the process n times to get to time t, but I generate many of them. I have L of them. So it's really like doing the parallel simulation. I generate many trajectories. I time slice here, and I say, I collect all these points. These points represent the random variable. Okay, you have to imagine that a random variable is just a collection of values. A random variable is just a sample. A random variable is a distribution. So if I want to build a distribution, I need many values that represent that distribution. The distribution, the histogram of the histogram of those values, if the sample size is big enough, will be close to this. It will be a good approximation of that distribution. Okay, we have many questions here. How can we find time evolved for stationary state and ergodic from? How can we find time evolved for stationary state and ergodic simulation from a single trajectory? We cannot. So the single trajectory simulation is only to get the stationary distribution. You cannot get with one trajectory. With one trajectory, you cannot get the single time distribution, because if you have only one trajectory and then you time slice that trajectory, you only have a single point. A single point is not a sample. You cannot build a histogram of a single point. Well, you can, but it's going to be just one bar for the histogram. This is why we're simulating many paths, because we want to build a sample of all these values. Okay? Think about samples again. We need to build large samples. So this is why we need to simulate many trajectories. For parallel simulation, it is better to use a random number generator with a long period. Yes, that's true. This makes sure that there's no correlation. Yes, that's true. And again, in Python, most of the random number generators are good quality with long periods, so I wouldn't really worry about this. Do not generate random numbers with different seed values at different processor. It might generate correlation. Yes, also these are all technical points about random number generators, which have to do with the fact that random numbers on a computer are not truly random. They are pseudo-random number generators, and so you might have some correlations between them. They're not perfect random number generators. These days, however, you can buy quantum-based random number generators, which are physical random number generators that have some guarantee of randomness, but this is not something that the mere mortals can have access to. Okay, and then the other question is a question about random numbers, so it's a bit technical. I think we can discuss this in the chat, but I won't be discussing this. Okay, what I want to do, and I'll finish with this, is that this is a simulation of, this is how you build a simulation of an SDE, and what I want to cover now is I've got the exercise sheet for chapter 5, stochastic differential equation, and then you have the numerical part, and then you have the stochastic gradient. That's good. And then you have the Kapitsa pendulum that I was discussing yesterday, which is quite interesting. So the Kapitsa pendulum, I'm just going to write the differential equation here, is a Newton's equation for some pendulum, which has this form, 1 plus a cosine WT, then sine theta, theta d, plus k theta dot is equal to 0. The k theta dot is the friction, this is the acceleration. The Kapitsa pendulum, again, I don't have a stick, but it's balancing the stick by shaking on the knee. If you go on YouTube and type Kapitsa pendulum, you get nice videos of people shaking a pendulum with a drill, and then you can stabilize a stick in the upright position as a stable position. So you just shake the bottom of your stick, and it stays stable in the position pi. If you push it a bit, actually it's stable, so it's a stable equilibrium. It's going to come back to pi, so this is quite amazing, and it depends on the shaking frequency, which is this one here, the omega. Okay, I'm not going into the derivation of this. You can Google this, you'll find derivations of the equation, the Newton's equation for the Kapitsa pendulum. What I want to do is to show a simulation of this where you shake at the bottom, so you have a frequency there, but also you're putting some noise. So you also jerk it with some noise. That's going to be Gaussian white noise. You can imagine that if I jerk it too much, the upright position will just fall, and so the stick will fall down. And so what we're going to do with the simulation is to find a kind of critical noise amplitude that will destabilize the stick from its upright, stable position. Okay, so let me go on sharing the screen now. It's here, good. Okay, I think you should be seeing the screen. This is the histogram. I'm going to go here now. I'm going to start first before I go to Kapitsa. I'm showing the simulation of Brownian motion. Okay, Brownian motion will be obtained where you don't have any f in the stochastic differential equation. The dx is given by dw, so x is purely a Brownian motion. So you see it here. This is the equation of the Brownian motion. The new state of the Brownian motion is the previous state of the Brownian motion times square root of delta t times a normal random number, which I obtained from numpy random n. Okay, I do this, my trajectories here have 50 trajectories. The delta t is, I take different delta t's and I simulate up to the final time 1. So here I take, this is the plot if I take a delta t which is 0.1. Okay, you see it's very broken, I just have broken lines. The delta t here is not small enough. This is not Brownian motion. So I change the delta t now to 0.05. And this is what I get. And here I have the Brownian motion for the time step 0.01. And now you see this is Brownian motion. I could take the time even smaller. I can do this. So it's actually 0.005. I can take 0.001 like this. And here's a simulation now with the 0.001. I think, I know there's a, sorry, I forgot to. Okay, there's an error in the subplot, I don't know why. Oops. For some reason this is broken now. It was working yesterday. Well, okay, doesn't really matter. This is Brownian motion. You have to choose a small enough delta t in order to simulate the process. What you see now is that, you see I have many trajectories. Here I have 50 trajectories. If I time slice those trajectories, I can collect the points for that time and then build a histogram. And this is what I'm doing here. Here I have a simulation of 10 to the 4 trajectories. I'm not showing the trajectories, and I'm building the histogram for different time. This is an initial time, this is a later time, and this is a later time. And so you see the histogram changes with time. It changes according to the Fokker-Planck equation. And here I'm showing the theory in dash, and the bar chart, the bar histogram, is the empirical histogram of my 10,000 trajectories. It doesn't follow exactly the theory because I have a finite sample. If I have 10 to the 3 trajectories instead, I have, no, it's because it's before. Sorry, I'm just not updating this in the correct way. Yep. I should have run the, okay. Yep. Good. 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 So here I have only 1,000 points, 1,000 trajectories. So you see the histogram has not the same quality. So if I want a better quality, I need to increase the number of trajectories. Now I'm using 10,000 again. It's going to take a bit more time to do the simulation, but then I'm going to see the result of this. It takes a bit of time. And then you see the histogram is better quality. If I go with more trajectories, I'll get something that exactly or more or less exactly follows the theory. If I use 1,000,000 points, 1,000,000 trajectories, it's just going to take longer. Okay? So this exercise is very useful because it shows how you should change the sample size to get better quality result, and it shows how you can time slice the trajectories to get the distribution at different times. Okay, and I'll finish with the last coursework, which is coursework number 5. And coursework number 5 is about stochastic differential equation. Here I'm loading different things. This is for stochastic gradient descent. I want to find the value of that global minimum, and there's a local minimum. If I use only a gradient dynamics, which is deterministic, then depending on the initial condition, I can reach either the local minimum or the global minimum. So what I do is I put noise into the equation, and I put noise in the way that I've mentioned yesterday. And what you see is that I can be in the local minimum, and the noise can push me in the global minimum. But if I don't change the noise amplitude, there's also a probability of coming back to the local minimum. And so I'll be just jumping between the local and the global minimum. So when you see this, you think, oh, maybe I should actually decrease the noise in time, and this is the idea of annealing. If you do annealing, then you get something like this. You might be in the local minimum, the noise will actually force a transition in the global minimum, and at that point, you should reduce the noise. Now, you never know, of course, whether you're in the global minimum or in a local minimum, but there are results in annealing literatures that tells you that regardless of the dynamics, if you decrease the noise slow enough, then you're guaranteed to reach the global minimum. Well, guarantee with some probability. Okay, and so have a look at this. This is quite interesting. You can play around with this by changing the annealing speed, the noise power, and so on. And then I'll finish with the Kapitsa pendulum. So you have the equation there. What I'm doing in the first simulation is I'm using a built-in function of Python called ODE int, which is an integrator for ODE. This is actually a Runge-Kutta integrator, and I'm just integrating the Kapitsa pendulum. So what I see here is the angular position in blue and the angular velocity in orange. And what you see is that starting from some angle which is not pi, I can stabilize the dynamical system to a position which is pi. And pi is the upright position. So in the simulation, I start away from the upright position, and by shaking the bottom of the stick, I stabilize the stick in the upright position. That's nice. Okay, and then you can play with this because now this is a deterministic system. You can change the frequency of excitation, which is omega. You can change the amplitude of the excitation. You can change the friction. And then you'll see that if the frequency is not right, you're not stabilizing the stick in the upright position. So it has to be in some range in order to have that upward stabilization. That's good. That's just a result of deterministic dynamics. This is just a result of ODEs. But it's quite interesting. It's nice to see this. It's got some chaos, and then you can have a look at this. Now, what I do is that I redo the same simulation, but now I'm adding some noise, and this is the noise I'm adding. So I'm integrating the theta and the gamma using the Euler scheme, and I'm putting some noise into the gamma because, as we've seen yesterday, you have to put the noise on the acceleration. You never put the noise on the angle itself. And so eta is the amplitude of the noise, and what I'm doing is that I'm changing eta. So eta is small, and it goes all the way to very small. And here I see I can still, now I'm showing only the angle. For some noise power, I can stabilize the pendulum around the position pi. So even if I have noise, I can stabilize the stick in the upright position. But in the highest noise amplitude, the stick now goes to the position 2 pi. 2 pi is the same as 0. So this is the stick falling down into the 0 position. The stick points downward. Okay, and then you can play with this. I can change the amplitude. For instance, I can put here 0.1 instead of 0.5. I hope the simulation will be working. Yes, it does. Here you see now the noise, the highest noise and the highest amplitude is 0.1. And here I stabilize around pi for some time, but then it destabilizes and it goes around the position 2 pi, which is 0. I can redo this simulation, of course, and then I'll get a different result because this is a random simulation. It's a stochastic process. And here you see now the pendulum as falling down into the position 0, which is the down position. And I can redo this. So this is very nice. Here, this is a simulation which is I've redone the simulation, and even though the noise is quite high, if you look at the red curve, I'm still stabilizing around pi. So you have huge variations around pi, but it's still kind of in the upright position. And this is possible because it's a stochastic process. So there are some trajectories that stay around the upright position. There's a probability that you still keep the stick stabilized. But this is unlikely. If you reduce simulation, you'll see that most of the time you destabilize the stick. Okay, and then how do you calculate the probability that you destabilize the stick? Well, you repeat the simulation many times. I can do 1,000,000 simulations. I'm not going to do this just by clicking. You really force the computer in doing a 1,000,000 simulation, and then you just count the number of simulations that are destabilized numerically, and this will give you an estimate of the probability of destabilizing the stick. What I'm doing for the last simulation is that I want to determine what is the threshold noise power for destabilization. So what I'm doing here is that I'm simulating many trajectories for different noise amplitude, and I look at what is the kind of the stable position. So initially for low noise, it's stabilized around pi, but around the noise amplitude 0.1, you see that 2 pi or 0 appear as a stable position. So this is the destabilization threshold. It's not quite clear because it's not a phase transition. It's really just a crossover from being stabilized to destabilized. And here, this is all done with simulation. There's no way I could study this in some analytical way because the equation of motion is nonlinear, and I have the noise acting on the acceleration. So you need simulation to understand what's going on here. Okay, I think I'm going to stop here. Have a look again at the coursework. I'm a big believer that if you want to understand something, you need to code it, you need to simulate it. This is the best way to understand physics, is to be able to simulate physics. And stochastic processes are, it's not very difficult to simulate them. I've given basically the basic methods for simulating Markov processes. These are, again, are just pointers. There's a rich literature about this. But from the methods that I presented, I think you can go deeper in any direction you want, either Markov processes in continuous time, Markov chains in discrete time, or stochastic differential equations. Good. Question. Let me have a look now at the chat. I'll finish the sharing. I'll change the camera. Okay. Okay. Any questions for the simulations?
Hugo, I had a question. So in this Kapitza pendulum, so when you go kind of above the threshold, so you say that then at long times you might, in some case, like you might go to the zero value, or you might stay at pi, right? Both possibilities are there. But it's not like if you go to pi, it's not that if you wait for sufficiently long, again you can come back. It's not like there's two kind of.
No, it can actually come back. So what I'm doing in this plot here for trying to pinpoint the threshold is I sampled points at different time because it's not like it reaches a point and stays there. So here you see for the low noise, I'm mostly around pi. For the high noise, I can be either at 2 pi mostly or at 0 mostly, but sometimes it gets back to pi.
Okay, so if I do a really long time average, I'll see it like 2 peaks around 0 and pi in the distribution.
Yeah. Okay. Initially, what I did actually for the simulation is to take the average of the path, but the problem is that if you average pi, 2 pi and 0, you get pi. So if you do the average, it actually gives you pi, so it doesn't really tell you if you're stabilized or not
Okay.
stabilized. So the average here is not really representative. Actually, what you should do is to build a distribution of all the
Right, yeah.
points, that you see, and then you'll see the destabilization threshold.
Okay, and this is not understood analytically, like, or is this is
I
known?
don't think so. I mean, I haven't really even seen this in the literature. I was just
Okay.
I used to teach ODEs, and so this is a nice system because you can stabilize an upright position, so it's kind of magical. Have a look at YouTube again. It's really nice to see that stabilization. Of course, we know about it, but the
Right,
thing we know is that if we stabilize a stick, we actually move it underneath as a controller. But if you just shake it with a drill with a given frequency, it stabilizes in the upright position. You just need to shake it fast enough, and this is why you need a drill to do this, or some kind of regular high frequency excitement. And so when I got to teach then stochastic differential equation, I was just curious. I put some noise to it to see if we could destabilize this, and you can. You see it here.
okay.
But it can come back. I mean, I think if I simulate this large enough, let's see if I can get a trajectory that comes back. I mean, it's kind of, you just, these are random trajectories, right? So I can go on and then see if it comes back. I think it would come back at, maybe the noise is too high. Maybe let's just put it at 0.5, 0.7. I mean, yeah, we could play for a long time here. No, yeah. You see what I mean? Yeah, it can come back. I've seen it before, but yeah, it's difficult. Yeah, so you see the point.
Okay. No, this might be around the transition, so you see huge fluctuations, but maybe
You see
above.
fluctuation, yeah. The amazing thing is that actually it goes to, this is pi. It doesn't go, so it goes to 4. So it's really really down, and then it's able to come back. So you have huge fluctuations, but the fluctuations are actually increased with time, and then at some point is a kind of threshold position where it cannot come back anymore. Yeah. So yeah.
Can you run it for like 200 or something?
Well, I can run it for 200, but the thing is that, oh, you mean 200 paths? Yeah,
Time.
you could change the simulation here. I'm just showing, well, what I can do is just as a hack, and I don't want to change the code too much, but I'm gonna have like 10 with the same noise power. 1, 2, 3, 4, 5, 6, 7. I mean, this is the stupidest act I can imagine. So here they're all the same noise power, right? Okay. And then you see those that actually get stabilized and not stabilized. So many of them are stabilized actually, but it seems that once you get stabilized, it's very difficult to come back. But it is possible. It's just very low probability, presumably. Yeah. Well, let's do this actually. I mean, I could do like NPA. Range, not NP zeros of ones instead. I'm gonna have 100 of them, and then this is the noise power. Well, this will be too long. Let's do 10 to see if this works. Yeah. So here I have 10. I'm gonna push this now to 50.
Okay. Can you also increase T final?
Yeah. So this is 50 trajectories now.
I think they just settle, right? They don't come back probably.
Yeah, I think there is a probability. You just need to take the time longer. The problem now is that I have that legend. Let me kill the legend. And then let's put the time. The thing is that now we're pushing the, so time 100 with the 100 trajectory. Yeah, no, they don't seem to come back.
So would it help decreasing the noise amplitude so that the probability of coming back increases, I guess?
No, I have to increase the noise amplitude. Yeah. So let's put it to 0.1 here. Okay, so here it stabilizes, but it doesn't come back. Let's increase it to, I'm sure at 0.5 now it's going to come back.
I don't think.
Yeah, here it does, right? Because now you have to see the periodicity. So 6 is 2 pi, and then it goes up to 12. What is 12? 12 is 6 times 2 pi, though. So
Also
it's still,
0.
but I think it might actually, it might transition with, here there's a kind of transition to another stable position, the upright position.
Okay.
Yeah. So I think you should have a look at this. So yeah. The noise might be too high, so, but did I have 0.5, 0.1, 0.2 maybe? But this is nice, right? Because these are long simulations for 100 trajectories, so you can see things. I'm not sure if I want to see the colors, but this is TV.
So they are segregating depending on what noise history.
Again?
No, these trajectories are segregating depending on the noise history, isn't it? Or
Yeah, they have different noise history. Yeah. Because they're all different. They're all random trajectories of the process.
But both are 0 finally, right? I mean, they just go in different.
I think so. Just trying to see the color
zero
here.
in a sense?
No, like the theta is modulo 2 pi, right? So it's.
Yeah, okay, yeah.
T label. Here I'm gonna just put like blue line, so they're all the same. No, where's the plot? Yeah, one blue. It's not blue. And what?
It's about the positional argument, actually. I think you should put it before label.
Yeah, I see, before the label. Blue line. There you go. Thank you. There you go. Yeah, so you should analyze this then to see which are the stable position and unstable position. I think this is a stable position here. This is another unstable position. So there's some transitions here. I think it depends on the noise power. Yep. So this has, I think, has been studied a lot in a different context. For instance, in coupled oscillators. So for instance, in fireflies, and then you want to, what is the noise threshold to prevent synchronization? The Kuramoto model actually also has been studied in that direction. So Kuramoto model is a model of synchronization, and then you can put noise to each of the oscillator to see when you have that destabilization threshold. I think this is just a simple example showing this with one variable. Good. Yes. If you have any questions, you can send me emails. I'll suggest again that you play with this. I have the instruction for how to install Jupyter and Python on the website, right? So if you go on my website, you have the instructions there. You can install also Anaconda, which is a standalone software, very useful for playing with Python. And then if you install Anaconda, you have Jupyter installed directly, so you can start this and play with the front end in your browser like I'm doing there. Jupyter is a very nice piece of software because it combines text and coding and plots, just like I'm doing here. So I have a look there. On my website, I also have some pointers to tutorials about Jupyter and Python. So have a look there if you're not familiar with Python. Python is an amazing language because it's free and it's used a lot by many people, especially in data science, machine learning. So it's got a wide usage. It's a very popular language. If you want to put something on your CV and then you don't have Python, I would suggest that you learn Python. Good.
I think there is a question.
Okay.
The last one.
There's no link to the Jupyter notebooks on the website. There's a PDF for Histogram, but no reference to Kapitza pendulum. So in the Dropbox, if you go into the coursework folder, you see there's a subfolder chapter 5. That's the coursework for chapter 5. And then you have, I believe, the Jupyter notebook for the Kapitza pendulum. So let me double check this. On the ICTS coursework chapter 5. Oh no, I forgot to put the Python notebook. Oh, I'm sorry about that. There's the PDF. Yes, there's the PDF for the notebook, but I haven't put the notebook. So what I'll do right now is to put all the Jupyter notebooks. So chapter one. I'll put the Jupyter notebook. Chapter 2. So these are not password protected. I'll appreciate if you don't diffuse them too much, because then I'll be in trouble when I get to start teaching the course next semester. All my students will have solutions. That's not nice. Oops. Okay, so now in chapter 5, I've put the IPython notebook for chapter 5. So you're going to have the code there for the Kapitza pendulum. Yes, it's not on my website because these are the actual solutions. So I'm not putting those solutions on my website, but they're for you now on the Dropbox. So the ICTS Dropbox. And I'll keep this until next week, and I'll delete this next week again, because I don't want to diffuse those solutions too much. You're free to use them. I'm happy to give the solutions to you, but I need to keep them secret for my own students. If there are students in the audience now who will take my course, I'm watching you. Good. I don't think we have more questions.
Yeah, there's a question from Prasenjit. How efficient is the gradient?
How efficient is the gradient SD technique to find the global minima in a higher dimensional potential energy landscape? It's a very good question. There's a huge literature on this. It's efficient to some extent, but it all depends on the annealing scheme that you use. So there's never any guarantee that you can find the global minimum of a high dimensional potential energy landscape, especially the very complex ones. You can always find a counterexample to any good techniques that you think you have. And so there's something called in optimization the no free lunch theorem that says that there's no method that will work in all situations. So I would say gradient SDE is kind of good, but it depends on the annealing. So what people do usually is that they do many simulations with different annealing schemes, and they try to see if they all converge to the same points. If they don't, then they just redo more simulations. And stochastic gradient descent is the method of choice for machine learning. So when you train a neural network in supervised learning, what you do is stochastic gradient descent. And that's been shown to work quite nicely. So it is quite, it's a good technique. It's a good technique because it's very simple. So it doesn't use swarm dynamics or any kind of correlations between different random walkers. It's just a direct gradient descent with a bit of noise to get you unstuck from local minimum. Okay, there was a question about what about atypical values of random? Are they simulations accurate enough to capture the tails of the distribution? So if you're interested in the tails of distribution, you just need bigger sample. The tail of the distribution means that the values there are very unlikely. So if you want to reach them, you just need a bigger sample. So you're going to see this in simulations. If you choose a small sample always to begin a simulation and then see what you get and increase the sample size from there. Never start a simulation with a billion sample. You're going to wait too long. Maybe there'll be a bug in the code, and then so the results you get are not good. So always write a simulation for a small sample size, well, smallish sample size to begin with, to make sure that the simulation is correct. And then once you're sure that the simulation is correct, then just increase the sample size to get better quality result. It just means that you're going to wait longer to get the results, but you'll get then more results in the tail, and then so you'll get some information about those tails. How to sample correlated random variables? Well, this is a subject in itself. Here we're sampling a Markov chain, so we are sampling states that are correlated. They're correlated in time according to a Markov chain. So a lot of the algorithm for sampling correlated random variables are based on Markov chains. This is something else. What we'll do tomorrow is use Markov chain not to simulate. We'll see methods not to simulate the Markov chains, but we'll simulate Markov chain as a computational tool. So we'll see, for instance, Markov chain Monte Carlo, even stochastic gradient descent. If you think about this, stochastic gradient descent, we're not interested in the gradient dynamics itself. We're only using a Markov process to solve a minimization problem. And so this is part of what we call stochastic minimization, the use of noise to compute something useful, like computing a minimum. You can compute eigenvectors randomly. You can compute zeros of functions randomly using noise. You can compute expectations. We've seen this. Good. I think that's it for the questions.
Yeah.
Okay.
So yeah,
Bye.
we'll see you tomorrow.